Yeah, it is start recording. Let's start then today's class. So we will first start from the things where uh, we have end in the previous class. So let's see where we have what we have learned in the previous class. So in the previous class we have learned that the sensitive dependence of the initial conditions, and let me go through the definition once again to then it will be more clearer, and with the example of with the help of the mathematical symbol. So let me write here. So we have learned that, so suppose there is a function f or a map f which maps this 0 comma 1 interval into 0 comma 1 interval. This map is called a compact map since it's map this interval to onto itself. So this map has sensitive dependence of initial condition. When suppose I want to say that I want to check whether or not this is sensitive, this map has sensitive dependence at point x, then we have to check that there exists a delta, a constant which is greater than 0. So and so this we have to choose the delta, and there for all interval I, open interval I, which contain this point x, where we have to check the function is sensitive or not. For all, if there exists a delta, a positive in a constant delta, and for all open interval which contain x, we find one y, there exists one y, at least one y, which belongs to this open interval I. And we also find an n which belongs to obviously natural number, such that it holds this condition that after n iteration the point x and point y will be at least delta distance far away from each other. So that then we will say that this x has a sensitive dependence, because wherever we how close we start from the x doesn't matter, there will always exist a n that will I will get an n and y, for which you will find that these 2 points are going far apart from each other. So that's why this x is sensitive dependence. Now we have also seen that what does it mean that a function is not sensitive dependence. So in terms of stability, that is called the Lyapunov stability, and with here for the if we replace all these for their exist symbol by for all and vice versa, we'll get that a function, when it is called, when we will say that the function is not sensitive at any point, at a point x. So then we'll say that for all delta constant greater than 0, and we will find an open interval which contains this point x, and for all I change their exist symbol to for all y that belongs to I, and for all n belongs to n, it will remain close to this x. That means therefore fn x minus fn y remain close to x. That says that these x you can infer the future of the system if the actual reality of the system is x, but due to your measuring device and due to owing to your computer limitation, you can only put a value which is approximated of x. Suppose that that is y, but we know that if it is not at all sensitive, then that for all constant whatever delta I will choose, I will find a interval. I will find an interval, and if I take any point from that interval, all that point will remain very closer to this x. So that is basically is called the Laplace is called it's called Lyapunov stability. It's called, I think, Lyapunov stability. So that's all. Then we have proved that then we have shown some we have seen some example where we have shown that a function that we have shown that a function which hasn't sensitive dependence of anywhere, that function is okay. So we have proved that a function f(x) equal to half x and does not have, we have proved that does not have sensitive dependence at 0. That's the thing. And interestingly, we have also seen that a function f(x) is equal to x square does have sensitive dependence at x equal to 1. Now why this is very interesting? Because I am saying that this is very interesting, at this is not a chaotic map at all. This is not at all a chaotic map. It's not at all a chaotic map. However, we find that there exists a point, and that point in the map has a sensitivity at that point. Still gone. Yes, that's far we have seen. Now let us see what is happening here. That's why it's become sensitive, and why any function becomes sensitive at all. So to do so, let me use a computer, a numerical method, from where I will want to plot this f(x) equal to x square and its multiple iterates, and from there anyone can guess why this is happening at x equal to 1. So let's see that. So this is my function. So this is very simple function, x square. Let me draw for x equal to 1. Okay. Oh no. Oh my god. And 3. Yeah. So you find that it's not that much steeper. It remain close to this identical line and it goes like this. Now one interesting thing happens when I will increase it. So let me increase 1 by 2 only, second iterate. So then what you will find, you will find that the function is become much more steeper around 1. It remain close to 0 up to near about 0.3, then it suddenly increases at a very faster rate. That means its slope become very higher, it's become very much more steeper. And whenever it becomes steeper, you will find that the distance between the point at x equal to something and neighbor point. So that means if I take any point from here, 0.8, suppose it maps 0.4, now near about close, suppose here it maps to 0.2, so only about 0.1 difference in the x-axis actually magnifies into the y direction at 0.2. Now if I increase and it become much more difference when we are starting from the initial condition x equal to 1, and if x equal to 1, if I take nearby any point, suppose point here, you will find that it is 0.6, around 0.6, and around 0.6 means only the 0.1 difference in the x-axis, and the second iterate makes this difference at is 0.4, 4 times more than the what is at the difference of the x. So now let me put it 5. So you'll find that it become much more steeper now. Now it just remained close to 0 up to 0.9, then it suddenly jumped to 1. So that means only now you see that the difference between 0.2 is magnified as 5 times of what is the difference of x. Difference of x is 0.5. now this difference increases as we iterate the map, and we have seen that after fifth iterate it becomes 5 times more. So that's why you will see that any point which remain closer to 1, whenever I will iterate more and more, that point will the distance between that point after the nth iteration will become larger and larger. So that's why it is sensitive at 0.1. so because of only that the sensitivity is only the artifact of that these curve become more and more steeper around 1. That's why it's become more and more, it's not more and more sensitive, it becomes sensitive at x equal to 1, that's why. Now the interesting question anyone can ask that that should come into our mind, that whenever we are saying that the chaos, we are saying about the sensitive dependence of the initial condition, and it is very natural because by definition what does the chaos means. So whenever we will say we know suppose there is a physical system, and we know the governing deterministic law of that system, and from that law we think that we can predict the future of the system. However, we have seen that very simplistic equation, suppose in logistic equation in this form, you saw that we cannot predict the future because of our incapability of giving exact initial condition due to the measuring instrument error or the precision error of the computer. So that's why, although this law, we know the law behind the system, how it's governing, how it's evolved with time, we can't predict exactly. So that's why we say the system become chaotic. So whenever we say the chaotic, the sensitivity comes with that. But in the case of this example, fx equal to x square, it is sensitive, but it is not chaotic at all. And this is the why is that. So the reason is that it's only steeper around x equal to 1. If you see that, let me draw it again here. So it's only become more and more steeper at n equal to 1. It does not become steeper at any other point. It remain flat, and it's close to 0 and in every point apart from 1. So that's why you can say that that's why only that at x equal to 1 it's sensitive, but on all other point are not sensitive. That means if I start in all other point, it will remain very close to that point. So that's why there is no, the predictability is there only apart from x equal to 1. You can predict all the other points. So that's why it is not we cannot say that the system has chaos in it. That's it. That's why it is not chaotic. So it from here we can conclude that the chaos does mean the sensitivity, but sometimes the sensitivity does not mean the chaos. And if we here only one point is sensitive, but if we find the every point of the domain of that map becomes sensitive, then we can say yes, indeed that system has some lose its predictability, and yes, there is some chaotic motion related with that. So that is the first thing. Now now in this class we want to see that how does this wiggle map, or we have seen that we have defined some map which is wiggle. So let me recall that definition of the map. So suppose there is a map which is a compact map. That means it it takes the 0 to 1, any point between 0 to 1, and it mapped that point at the interval 0 to 1. So that's why its domain and codomain is same. So it is compact map. And if we compact, and suppose in between 0 to 1, there is a point C. In between 0 to 1 there is a point C. There is a point C, and this function f is continuous and increasing from 0 to 1. From x, f is increasing 0 to 1 when x goes from 0 to c, and it is continuous, and f is continuous and strictly decreasing to 1, is strictly decreasing 1 to 0 when x goes from c to 1. So that's it, called the compact one hump map. So this is called compact one hump map. And from that, what we have seen in the previous class, and I have also mentioned that lemma is very important. That is called the spike lemma. So what, and from the spike lemma we know that for a one hump map we can get the steepness as much as we please around any point of the domain. So that means for one hump mapping, and one example of the one hump map is logistic map. So for any one hump map we can safely say that any point whatever we want, if I take any point and we'll find some n, and if we increase the n, the steepness of that curve will increase, and the steepness can be increased as much as we want. So that means it will have some sort of sensitive dependence at every point, and in this in that domain, if the map is one hump map and it is compact. Now let's see what and we not only do that in the series of lectures. We will also prove that and this map is called wiggly map. This one hump map, and this is, since one hump map means one hump compact map means it will contains two things. One is at nth iterate it will have 2 to the power minus 1 hump, and second that the largest base of any hump will decrease as n tends to infinity. Since these two property will be held by this one hump mapping, so this map will also called the wiggle map. And its name is wiggle map because it's wiggle up and down as we iterate in, as we increase in the map will wiggle between 0 to 1 and 1 to 0 in the domain. So that's why it is called wiggle map. And since the wiggle map has a spike lemma, because of that we will have the stiffness as much as we please. We can have sensitive dependence at any point in that map domain. So we will in this class will prove not only the sensitive dependence but also we will prove that that transitivity and see that a dense set of periodic points. So let me recall what the spike lemma, and from that spike lemma we can easily prove that the sensitive dependence. So let me recall it. What does this spike lemma is? So spike lemma means if F is a compact map, that means it map the interval 0 1 to an interval 0 to 1, that means its domain and codomain is same, then we know that have wiggly map, wiggly iterates and for every interval I, for every open interval I which is a subset of 0 1, there is a hump. There is a hump of some iterate fn whose base is contained in I. So that means whatever interval we have choose, suppose we chose in between 0 to 1. Now this lemma says that whatever interval choose, no matter what interval we choose, how small interval we choose, we will always find one hump of some iterate fn, that base, that means it will remain inside this open interval. So suppose that open interval is, for example, between 0.5 and between 0. It's not very good sketching, but let's assume that this is 0.5 and it is 0.55. In the interval of 0.05, if we want to means if anyone want to have a hump which contained in this interval, he will get that hump. So you have to only find that iterate n, and if I increase the iterate n, we know that this wiggly iterate, the base of this iterate will decreases. So after a large enough n, we will obviously get an hump in any interval whatever we want. And one thing is notice here, so why it is called the spike lemma, we have already discussed that since that it become more spiker whenever we increase n, it become more and more spike like structure, so its base will decrease and it has to attain the point 1 and it will decrease to 0 again, and whenever the base will the base of the hump will shrink, the steepness of this point will increase much and much more. And this property, you will see this property will manifest this sensitive dependence. Let me give an lemma, then I will prove this lemma. So if f is a compact map, that means it map 0, 1 interval to 0, 1, has weakly iterates, then f has sensitive dependence everywhere with sensitivity constant up. So let me again recall that the method of proof. So what is the definition of the sensitive dependence? So there we will say there exists a delta which is greater than 0, a constant which is called the sensitivity constant, and we know we want to prove that it has a everywhere sensitivity. So that means for all x which belongs to this 0, 1, and for all interval which contain the point x, there exists a y, we will find a y in this interval I, and we will also find an n, obviously it belongs to this natural number, such that the distance between the nth iterate of x and y becomes at least this delta apart. So it says that if I take any arbitrary point in this x-axis here, and whatever means whatever small interval you choose, suppose you choose very small interval, we will prove that for every interval which contain this point x, for every interval you will find a y, for which you will say that there exists n, and you know that these the iterate of this x and iterate of this y will become delta apart from each other. So that's why it is called the sensitive. Whatever close you go, whatever neighborhood you go in the x, you will always find a y, and you cannot say in general about the future of x from the y. So that means the predictability has been lost already. So if we can prove that, so let's prove that. The line of the proof is very simple. So and we will here we'll see, since this delta is there, so we know the delta is up, and to prove the sensitivity, the main hard part is to find a suitable delta, but we know already the delta is up. So let me prove that. So let x be any point in the interval 0, 1, and let I be any open interval in 0, 1, and obviously it contains x. Now we will spike lemma. So since we know that from the spike lemma is, and the lemma says that the map is wiggleted, that means it will actually satisfy this spike lemma. That means it is suppose 0 to 1 interval, 0 to 1 here, suppose 0 to 1 here. Now suppose that this is an open interval I. So I know that suppose this point is, suppose any point is x, so we know that there will be a one hump because of this spike lemma. We know that it's whatever means whatever open interval we choose, we will always find one hump. So this is 1, so we'll always find one hump whose base is contained in I. So that is from the spike lemma, that we have already proved in the previous lectures. So now, so this is corresponding to some iterate, suppose fn is iterate. Now suppose your x is here, so let me use another color. So suppose this is your x, and suppose this is half, and you will see that why I'm drawing this half line. It is required for the proof. So suppose your x is half and your x is cut this point, suppose some point, suppose some y, and you know that this y is, since this is the curve of fn x, this is the curve of fn x, you know that y equal to fn x. Now two cases could be possible. One is that I have shown here, that means this fn x is less than half, because it's less than half. Now you see that interesting thing here. Let me use another color. You could always choose a point in this interval, because in this interval you will find that there will be some x which actually maps f of that things actually maps 1. So suppose you will get here some point, let me here take it x something, suppose x prime. You will, here it is, this point is x, and this red black dot is x prime. You will find you always get a point x prime which actually maps to 1. So you will find that this, suppose this is 1, so that means 1 is equal to fn x prime. From the spike lemma you know that one hump is there, and one hump means it will goes from 0 to 1 continuously, that it will come back from 1 to 0, and from the spike lemma we know that it contain in 1. So that means that guarantee that this there will be a point in this hump x prime which actually under the map fn goes to the 1, and then we are done. So here for fn x is less than half. Now you see that means that fn x prime minus fn x is equal to 1 minus some y, and since y is less than half, that means it becomes, fn x prime minus fn x will be always be greater than half. So the first thing we have proved. Now the same thing we will prove. Let me copy it and paste here. Paste it here. So you can now I will prove that for x equal to, when fn x equal less than half, we have proved that I will always find some n and some y for which this condition satisfied. And if we can prove that this is also true for fn greater than half, and you can see that this is equally means it's very easy to prove that thing. So greater than, suppose it is greater than half, so let me suppose now okay, now suppose my point is not this x, suppose my point x is here somewhere between, whatever you choose, here suppose I choose x, and it maps, oh let me draw, my drawing is very horrible, okay, it is means point somewhere here, suppose here, okay, suppose it points here, suppose now this become y, so suppose your x is here, it points, that means if y is fn x, and which is greater than half. Now you say that what x prime I have to take for prove that statement, this statement, it has to be greater than half, and it is very simple. So we can always choose this point where we know that since it's spiked from the spike lemma, we know that it contains one hump, and one hump means it goes from 0 to 1, so that means this point will also be there. Suppose this point is x prime, now we have to take this prime, this point is x prime, so that means 0 is fn x prime, 0 is fn x prime, so that means I can take this point, so that means there exists a point. Now let me show you the difference, fn x minus fn x prime, so that is actually greater than half. So you see, whatever its fn x is greater than half or fn x is less than half, doesn't matter, it actually always satisfy this fn x minus fn prime x prime is greater than half. So that means we can always, whatever interval you gave me, we can always find there exists always a point y, or here I use x prime in that interval, and there exists a n for which this is satisfied. So that tells us that any compact one hump map will be sensitively dependent to the initial condition. That is the thing, and one of the example of this sensitive one hump map is very simple, that logistic map. So that's it. Now let me, that's it. Now this is it. So let me show you something. So we have told that this is not only this sensitive dependence, but also transitivity is there, and dense set of periodic orbits points is there. So let me go towards that. So let me begin with that. So let's say dense periodic orbit, dense orbits, and transitivity, dense orbit and transitivity. So although the sensitivity is generally agreed to be one of the most important feature or ingredient of the chaos, there are other ingredients also which are also very important to the chaos. That is the two things that I have here written, the dense orbits and the transitivity, that are very relevant also. Though let me recall that what that sensitivity means in words. Though sensitivity means that if I take any neighborhood 2 points, if I take any nearer 2 points, this suppose x and this y, and the sensitivity says that the orbits of these 2 points will become far apart from each other when I iterate this n. So when I will iterate, these 2 points x and y will become far apart from each other, and this is the sensitive dependence. But here you see one thing is missing, that to prove the chaos we have to always say there we have to take 2 points. To see the chaos we have to take 2 points, because if we do not choose 2 points, we cannot see that what the points are becoming far apart each other or not. But the thing is, whenever, if you recall that whenever we are plotting the orbit diagram, and from that orbit or bifurcation diagram we are concluding that the system has chaos for particular value of that parameter, then you can remember that there we conclude something, that there are in the region where the set of points become very dense. So if I go there, so it is like that, then there, then something happens, then here a very dense things of point, and we say that the chaos is there. And why we are saying, why we have said that the chaos is there, because we know that in that region something remarkable happened, that is becoming that the orbit is actually very much aperiodic, very much it's not predictable. It actually wanders all over the domain, all over the codomains between 0 to 1. The orbits never settle down to any fixed attractor, any fixed orbits, any fixed points. Rather, it actually wanders, roam around all over the codomain. So from there we conclude that this becomes very hard to predictable, because it does not settle down to any kind of orbits or fixed or any kinds of fixed points or periodic orbits. So that means in itself that dense orbit means the chaos. So dense orbit means the chaos. So the orbit seems to chaotic. Let me give an example, then it will be much more clearer. So intermittency. Yeah, here you see that for this is a logistic map. I use r equal to 4, and you see that for r equal to 4, this orbit is actually seems like chaotic, but I haven't proved 2 point to see whether or not this system is chaotic or not. But from here we can see this is very much aperiodic, it seems unpredictable. So that's why by seeming it's look like chaos. And what here in these dotted lines you can also see that after first iteration it going some here, after second iteration it going somewhere here. So you see that it roam around the codomain axis 0 to 1. As we iterate, it wanders around this codomain axis very densely. If I, instead of 50, if I draw, suppose draw, okay, let me draw hundreds, maybe 100, you will see that this axis will become very dense where this graph is. Now see, you see here these points become much more denser. So it is never means whenever I just increase the iteration, it become much more denser. That means it wanders around all the codomains. Some point some iterate it will give value here, some iterate give value here, some iterate here. So never repeat itself, the pattern not repeat itself, it roam around all over this codomain. So that is actually chaotic also. And what is the nature of the chaos, what is the signature of the chaos, which we can see here? It is the denseness of these orbits, denseness of the orbits. as we iterate. So this denseness also means chaos. So this denseness is as an important property or important factor for the chaos. So how we actually define denseness? So I will prove that denseness in the next class. So let me only show you that what is the meaning of the denseness uh, in terms of graphically. Then we will define it in the next class. So let me draw it. Or maybe 10, 20, 15. Okay, let me do one thing. Okay, now yeah, now let's see. Now denseness, what does this denseness means in mathematical term? Denseness means, suppose you take a interval. So here you see that a open interval is between 0.7 to 9. So 0.2 means its interval is around, length of the interval is 0.2, but in the codomain you can see I am taking an interval which remains between these 0.7 to 0.9, and this is, suppose that this is an interval j. Now you will say that the orbit is very dense if you can prove that if I take any point, any value of x, suppose 0.2, 0.3, 0.4, doesn't matter, any point of x, I will say definition is there exists a n which for which you will find that f n x, that if I iterate n time, that point will ultimately go inside this interval. Here you can see the n is 4 for 0.2, the n is 4, and if n is 4 you will find first that there is a point of this iterate. If I f 4.2 is between in this interval, so whatever point you take, you will always find some n, it will visit this interval. So that's why it is called the dense, means it will visit any neighborhood or any interval. This means whatever, any point will visit any interval in that region. So it will, that means it will goes everywhere, it will goes everywhere in the codomain region. So that that what will make the orbit looks very dense. So that's it. Now that's it for the today. Now in the next class I will show you the proof of this denseness and mathematical the definition of the denseness. And I also, this is the dense periodic orbit, or it is similar, same as we will see in the next class, that this denseness, the proof of this denseness is very hard. Not very hard, we need some concept like topological, more topological things that we haven't learned in this class. So I will prove that thing is called the transitivity, and also will prove that the dense periodic points, that I'll prove that there exist dense periodic point. That's it. Okay, then thank you. Then next class we will meet again in the next class at Monday from 11 a.m. So thank you. Let me now quit this lecture here now. So let me, there is